In the previous video, we tried to reduce the satellites having the elevations angle around 30 and higher. So we would like to reduce the number of satellites in this way. So as you recall, we have this configuration of the satellites, so scattered across the horizon. So we now want to reduce the satellites to 5. So for example, by putting a constraint that the satellites having the zenith angle around 60 degrees will be omitted. So for example here, or the elevation angles lower than 30 degrees will be omitted. So the problem in our previous setting was that the data cannot be read by the Octave. That's why I did write a new matrix, or a new observation matrix, and also coordinate matrix. So I am then commenting out these satellite coordinates, and I will use the satellite coordinates. So 5 satellites will be used here in this case. So let's have a look. And so you see we have less satellites here. Now let's try to compare the PDOP and GDOP values: precision, deletion of precision, geometric deletion of precision, and positional deletion of precision values. So you know the geometric one is the trace of QXX, and the trace, but I should take the square root of this trace. So in this case, as you see, it is around the value of 4. In our previous case, with 13 satellites, so we had obtained this value to be around 1.6, as you recall. So now let's define a QP matrix, and the first 3 elements, or the 3 by 3 submatrix of the QXX matrix will be chosen. In this way, we can again compute the trace and then take the square root. So this will correspond to positional deletion of precision, as you see, and this number was also 1.4 previously, but now you get to 3.3. So for example, in a street case with high buildings, if there are high buildings along a street, so you can only see the satellites in the zenith direction. So that's why you will then get less DOP values, or deletion of precision values. So that's why we use these deletion of precision values for the satellite geometry description. So the larger values will result in lower root mean square error values. That's why we can make some plans for the observation, and we can make some arrangements for our observation. Now let's have a look to our 10 satellites case. So let's use again our 10 satellites case, and let's have a look to the accuracy and the satellite coordinates. Sorry, the position, the null coordinates in x, y, and z direction, and the accuracy thereof. So now you see here the accuracies the XYZ 0 here will denote the adjusted Earth-centered, Earth-fixed coordinates, and the now the standard deviation of the coordinates then will be diagonal elements Q, XX 1 to 3, 1 to 3. So if we take the diagonal elements and then take the transpose of that, sorry, so now you see this is the coordinate given here, and this so these are the coordinates, and these numbers are the accuracy of the or the root mean square error of the Cartesian coordinates. Now, as you can see, we can obtain 3 to 5 meter accuracy or root mean square error by using point positioning. So this point positioning is not enough for geodetic purposes, because we mostly need centimeter level accuracies. That's why we must use relative positioning. In the relative positioning, the pseudo ranges are used, but in addition to pseudo ranges, we also use phase observations. By using phase observations, then we can get the centimeter, and in cases even a millimeter level positioning is possible.